In the previous video of the Introduction to Embedded Systems series, we have seen the basics of embedded systems, what they are, how we build firmware for it, how we run it, etc. And in this video, we're going to see some more advanced stuff, like embedded operating systems, debugging and logging, and other things. If you haven't yet seen the first video in this series, I strongly recommend that you do that first, and here is the link to that video. Otherwise, just keep going, and I'll see you after the signal.
We have built our firmware and we have executed it, perhaps even pre-silicon. Will our firmware include an operating system? Operating systems can give benefits ranging from scheduling threads to file systems and security features. Some embedded systems are simple enough to not require an operating system and can do with something similar to an Arduino loop, some interrupt handlers, and that's about it. However, even systems under the umbrella of small embedded systems may sometimes be better designed using an operating system. When that happens, the difference between big operating systems and embedded operating systems comes to play. Unlike the three titans we know from desktop machines and smartphones, and Android is based on a Linux kernel, there is a vast number of embedded operating systems that can be very different from each other. This is a very partial capture of the embedded operating systems list from Wikipedia. You have dozens here, and that's only a small part. The various embedded operating systems are very different from one another. As always in embedded systems, it is up to the designers to choose the right OS or decide none is needed. Embedded operating systems can be as small as FreeRTOS, with a memory footprint of just several hundred bytes and mainly just thread scheduling and synchronization, to behemoth like embedded Linux, with systems like ECOS and more in between. Additional features are configurable footprint, storage manager and files, memory management of various sorts, processes support, networking, and so on. Besides size and features, the architectures of those various operating systems could be very different. Take a look at the Android stack and how the OS is pretty much the governor of everything. This is typical to big operating systems. A small and embedded operating system could potentially be a more rights-equal component in a system design. In the block diagram on the right, the drivers and file system work like libraries to the applications, while the OS can, for example, only schedule and synchronize threads and have minimal role, unlike the manage all systems. So you can expect very different architectures, with those being only examples. And as always in embedded systems, the solution designer has to choose the right solution for the defined problem at hand. As one can already guess, debugging embedded systems also entails special challenges. Let's look at some of those now. We build our code on a development machine and we run it on a development board. Unlike the big OS we have on the desktop machine and other software infrastructures we have for debugging, on the dev board we only have the minimal code we need for execution. This is unless we have installed special provisions in firmware. Actually, we are external to the dev board or the embedded system. On big computers, we as developers operate on the same machine that runs the developed software. This is not the case for embedded systems. How are we going to connect and see what is going on in there? We don't typically have a monitor connected to embedded systems, so what about seeing debug prints? What about the debugging facilities we may be used to? Can we set an infinite amount of breakpoints? How about using watch points? So the way to debug embedded systems is to first connect to them from the outside. Every CPU has a JTAG mechanism embedded into it that allows, among other things, control over the execution. JTAG can be used, for example, to set a breakpoint on an address or to read memory from an address. In this picture, on the left is the system under debug, which is based on an AVR microcontroller, while on the right is the AVR Dragon, the physical layer connecting our desktop to the AVR's JTAG. And here is the full setup. With such a connection, we can set breakpoints, read and write memory, and more. So going back to some of the issues we have raised before, debugging an embedded system can be quite different from debugging on a big system. We have a direct connection to JTAG in order to debug things from the outside. The lack of prints can be solved in several ways. One example is printing to memory and reading it out with a debugger, and later we will see more on that. And yes, we may have limitations like a small number of possible hardware breakpoints, no watch points, also known as data breakpoints, and more. We now move to the subject of logging, which is a close relative of debugging since logs are many times used as a debugging facility. However, logging is more than just a debugging tool, and hence we have a special section for it. We use logs for several things: getting an idea of what is going on in the system, debugging, profiling, and perhaps more. But embedded systems are closed systems by nature. How are we going to get out our logs? One solution is the Arduino way. The system is sending out logs over the serial connection, and an agent on the desktop machine receives and presents them. Not every system has a serial connection, however some systems have dedicated hardware that is tasked with sending out those prints from within the embedded system. Such hardware can be superior to serial in terms of security, for example. Another option is to write prints into memory and then to extract it with a debugger through JTAG. This is of course way more limited than the previous solutions since we need to time the extraction of the logs, and for example a system reset will wipe the memory, potentially before we had a chance to extract the logs. Another option is writing logs to flash. This is generally a good idea to do some logging to flash regularly, since flash survives system resets and power losses. However, too much flash logging can shorten the life of the flash device. Logging to flash will look like this. Assume you have got the image onto the system by any means that we have described before. Now let the system run. The system will write log entries to flash as you designed it to do. When the time or the need comes, pull out the content of the flash using an ISP or any other mean. You may now have to analyze the image, get your logs depending on how you have placed them in the image, and parse them if necessary. Potentially, you have chosen to store them compressed on the flash, in which case you will also have to uncompress them. Now we get to one of the most heavyweight subjects in embedded systems: field updates and bug fixes. Assume we have fixed a bug, perhaps even a security vulnerability. How will it get to units that are already deployed in the field? In regular software, this is an easier task. Big systems are connected and also operated by a user. You can interact with the user and get his participants in the process. You can indicate errors to him, and in case of a catastrophe, the user can help in the recovery, for example by reverting to an older version. Even in a total Armageddon, for example a failed fix in a critical part of the OS, there is what to do, and in the worst of all cases the user will lose unbacked data but reinstall the software and get the machine back to life. In embedded systems, if you apply a fix and it's not working, the damage can range from permanently losing crucial user data to making the system completely unusable, also known as a brick. So if you don't want your deployed systems to look like a brick graveyard, be very careful. When systems are bricked, the user must either throw them away or get them back to the manufacturer for refurbishing. Not something that will add a lot of health to your company. What can make this happen? For example, if you accidentally deleted crucial files during the update, files the system cannot do without, or you have messed up something and now the system keeps resetting itself. For the user, the system is unusable even though it is alive. Google, Apple withdraws watchOS 5.1 update to find a nice article about how Apple bricked watches look like. We assume an update is going to happen by an internal firmware component receiving new binary elements to update the system with. We need a medium to send the updates over. The new king today is over-the-air or firmware over-the-air. Another option is to ask the user to download an update image, and assuming our system has an external USB connection, to update through it. A wired connection is also an option. Whatever medium we use, the process must be atomic. Atomic means that either the process is completely successful or else it is fully reverted to prevent malfunctions or even bricks. This mostly means that the update process running inside the embedded system cannot remove the old elements until the newly updated elements are fully and successfully present on storage and the system can surely boot and function with them. How would the system know that the new firmware works? By applying tests, ranging from just a successful boot to running a BIST, built-in self-test. Beyond just being correctly functional, the update process must also be secure. We cannot let our system be taken over by a rogue update. This means that the system must take in only authenticated updates, authenticated by digital signing. One more strict requirement: do not destroy or corrupt the user data, for example by overriding it. We talk about things like saved settings, passwords, or files. If you do corrupt or destroy the user data, the system may still work, but the end user is damaged, and the purpose of the system is defeated. Let's talk about another issue that is more important in embedded systems than in big systems, and that's survivability. In the general case, even if not always, an embedded system will be operating without user interactions. If it goes down or malfunctions, it may be unknown to anybody or just impossible to handle. For that reason, extra thought has to be invested in how we create a survivable and robust system that can preferably avoid and potentially get out of trouble. We will take two representing questions and investigate them. The first is, what happens if our system crashes? Assume we have a bug somewhere and there is a deadlock. Our system may not be able to respond to external commands anymore, and everything is stuck. Is there anything that can be done? Is there anything we can do to make the system resilient to power losses? Or will sudden power losses corrupt our system and render it useless? Let's refine this question. What happens if a power loss strikes in the middle of writing a file? Perhaps a reset occurred, the battery was depleted, or any other reason. We may now have a file that is in practice corrupted. What are the consequences to the system? In the solutions department, the first element we're going to discuss is the watchdog timer. The watchdog timer is a piece of hardware we can have on our system that can function as a liveness checker and reviver. Here's how the watchdog timer works. We start by enabling the watchdog timer, typically during system boot, with some time constant t. The watchdog timer will wait for our liveness signals and react in their absence, as we will see shortly. To signal the watchdog timer the system is alive, we rearm the watchdog timer. This is done repeatedly to continuously tell the watchdog timer we are okay. One way to manage the rearm actions is to make it the responsibility of a thread that is assumed to get a time slice at least every t time. The assumption is that if the system is hung, the thread will not get to run and will miss the t time window. Of course, this scheme is true only with a careful design, and of course there are other ways to try and detect hands depending on the overall design. This is just an example. If the rearm window is ever missed, the watchdog timer device can respond. For example, it can trip an interrupt and let our interrupt handler handle the situation. Alternatively, it can reset the system to try and get her out of the bushes. Some designs do both. First, trip and interrupt as a soft response, and if the rearm window is missed again, reset the system. Now let's approach the second question, power loss handling. Back to the example of a power loss during a file write. Can our system tolerate this, or will it consume the bad data and somehow recover? One way to approach this is to never let the data become corrupted in the first place. We do that by creating a storage layer that guarantees atomicity of file writes. How? By bookkeeping every step in the file write process. The bookkeeping data itself is saved on non-volatile memory so we can read it during boot in case the system went down due to a power loss. If we have recorded the file write step this way, on our way up from the power loss, we can also know if we went all the way through with the file write or if we were cut somewhere in the middle. In that case, we can do cleanup operations to remove side effects. So yes, the file will behave as if it was never written, but at least we will not consume corrupted data. The same logic can apply to other flows as well, perhaps basing higher level flows atomicity on the atomicity of lower level facilities like an atomic file system. As a characteristic, this is called fault tolerance. We can say a flow is fault tolerant if the system can survive a fault in the middle of it with no side effects. This is a strict definition. One can also define a good enough behavior for a system, so it can be called fault tolerant as long as it lives to this defined bar after a fault has occurred, even if there are leftovers. Of course, fault is also something that has to be clearly defined when saying a system is fault tolerant. Obviously, not every imaginable fault is tolerable. It is a matter of definition.
So at this point you must be scratching your heads, asking yourself where is one of the most important parts of any system, and that is security. And luckily, there is a video just on that coming up. Please like and subscribe and you will be notified whenever this video becomes available, as well as other great stuff about embedded systems. See you!